Is the screen visible to everyone?
Yes, sir.
Yes, sir.
So,
Yes, sir.
Yeah.
Yeah. So we'll be taking up a revision of the multivariable calculus part of the course, which is covered in the content of week 9, 10, and 11. So linear algebra is already done, right? That there were 2 revision sessions earlier in which uh, linear algebra part is completed, I assume.
Yes, sir, it is.
yes, sir.
Okay, I'll try to focus mostly on theory, the revision of the theoretical concepts, and the problem solving will be done in the TA sessions. There will be problems in between just to make it not too abstract, and as usual, if there is time at the end, we'll take up a problem. So the basic thing that we do in multivariable functions is take the concepts that we already know in the context of single variable functions and then try to generalize them to more variables. Not everything can be done as it is, so we will make natural generalizations as and when we encounter them. So just to recollect, you know what it means by what we mean by a function of one variable. It's a function in which you have one input and one output, one real number as an input and a real number as an output. Most of the time we take functions from R to R, but in some cases we restrict it to certain domains as per the requirement of the problem statement. So a scalar valued multivariable function is a generalization of this thing, wherein we don't only ask for or require that there should be a single real number as an input. There may be 2 or more real numbers as input, and the output is a real number. And such things are called scalar valued multivariable functions because the value of the function lies in the codomain, which is R, which is a scalar number. But if you allow the output also to be a vector, which is an m tuple of real numbers, such a function is called a vector valued multivariable function. So scalar valued or vector valued, this is in reference to what is the codomain. And then multivariable means your domain.
Sorry to interrupt you. Good evening, sir. Actually, there was stats 2 session. I just joined, got late. Can you, sir, repeat where we have started?
This is the first slide. This is basically the first slide. We are just building up the what is a multivariable function and scalar valued multivariable function and vector valued multivariable function.
Okay, just request to just repeat the, sir. Will be grateful, sir.
Yeah, sure. Functions of one variable is very well known, where you have thing like f from d to r, where your input has one real number and output is one more real number. Now, the generalization of that is a scalar valued multivariable function, wherein you have n inputs and one output, and n real numbers as input and one real number as an output. That is called scalar valued multivariable function. And an even more general framework is that of vector valued multivariable function, where you have n inputs and m outputs. So these are the things that will be working. And examples of multivariable functions, linear transformations, as you know, are maps from some Rn to Rm. They could be some vector space to another vector space, but in a specific case of the vector being Rn or domain and codomain being Rn and Rm, you have linear transformations to be examples of multivariable functions. And then if you have certain multivariable functions, then the sums of them, the scalar multiples of them, products, quotients, all of these things are multivariable functions. And polynomial functions, for example, in Rn, polynomial functions, projection functions. These are all basic examples. But by now, I'm sure you are familiar with what a multivariable function is. So let us move to the next concept, wherein we mostly say why we restrict our attention to scalar valued multivariable function, because given a vector valued multivariable function, so if I write something like f of x1 up to xn, this is some m tuple, right? I can write this as f1 of x tilde being this x1 up to xn. I can write this as an m tuple. This should be m. Now, x tilde. So each component, you can split the vector valued function as m component functions, each of which is a scalar valued multivariable function. And then you can analyze that, and then you can, so it is, for most cases, it is sufficient to look at scalar valued multivariable functions, which we'll be doing for majority of the, if not for all of the remaining portion. So as usual, x tilde will be used to denote the vector x1, xn in Rn. This is just some setting up. Now, one of the things in calculus, one of the important things in calculus that you do is measure the rate of change. And the notion that is there is that of a derivative. But in this case, in the one variable case, you know that there was only one input and one output. So you can measure the rate of change of that one real number output with respect to that one real number input. But in multivariable, you can't do that because you have multiple inputs, right? Scalar valued multivariable functions also have multiple inputs. So to formulate a reasonable notion of derivative, we have initially what is known as the partial derivative, which we will now define. So this limit, as you know, the existence of this limit for a one variable function is what gives you the notion of derivative. And this is to be interpreted as change in output divided by change in input, because f of a plus h minus f of a, the numerator, that is the change in the output as we go from a to a plus h. And the change in input is actually h, which is, you could write it as a plus h minus a if you want, right? So this is output by input, and then you take infinitesimal change of the same. So this is the one variable case. So what do we do in the multivariate case? We take each variable separately and then try to do the same thing. So this gives rise to the notion of partial derivative, wherein I have a scalar valued multivariable function, and I change the function value only in the direction of ei. So this a tilde is actually some a1, a2, an, right? And what I'll do is I'll only add something at the ith coordinate. This is the ith coordinate. Which can be written as HEI, right? So this 000H000 can be written as HEI. And this will change the function only, the input changes only in one variable, which is the ith variable. And then I do the same thing. I measure the rate of change as I go from a tilde to a tilde plus HEI, and then divide it by the change in input, which is H in this case. Once again, you could write it as a tilde plus HEI minus a tilde, which gives you HEI, but the norm of that is 8 is just H. So the change in input is just H, and the change in output in the direction of EI is f of a tilde plus HEI minus f of a tilde. And this limit, you have to verify that this exists. This need not exist always, as we will see in many examples. But if that limit exists, then that is called the ith partial derivative. In most problems that you will encounter, there will be just functions of 2 or 3 variables. So you will be dealing with only things like partial derivative in the x direction, y direction, z direction, but this is the general framework where we define the thing for any EI, any the change in or the partial derivative with respect to any variable. Right? Now, this is an example that I have chosen to analyze carefully because this like understanding this example gives you a fairly good understanding of the partial derivatives, next directional derivatives, and so on. So I have this function fxy given by xy divided by x square plus y square when xy is not equal to the origin, and it is defined to be 0 at the origin. You cannot just substitute 0, 0 in the first expression because the denominator becomes 0, correct? So it is defined differently at the point 0, 0, and outside it is defined as something else. So we have to check what is, let me see if I know I'm not at one. So it will be what is, let's say, fx at 0, 0, fy at 0, 0, and fx at xy, which is not 0, 0, if you want. Fy, xy. Ah, oh, this is xy not equal to 0. Now, what do? We try to compute the limit of that expression. What was that expression? So for fx meaning, so remember that, okay, this is also a notation. This would be, so this has to be xi. That's a typo. And this would be written as fxi of a tilde. Fxi of a tilde means the partial derivative of f in the direction of xi or in the coordinate xi at the point a tilde. So here you have the direction to be the x direction, the point to be 0, 0. So the thing that you have to compute, just a moment. Right. The thing you have to compute the limit of is f of 0, 0 plus h times. This is the standard vector in the first coordinate minus f of 0, 0. Let's see what I was. Yeah, divided by h. This is what we have to do, correct? If this limit exists, then my fx of 0, 0 will be equal to this.
Sir, why you take 1 comma 0?
So fx means it is fx1. So as in here, we don't write x1 to xn. We write it as x and y just because it's two variables. In general, we write it as x1 to xn. See over here, with respect to this xi, right? With respect to xi, it is a tilde plus hei. And in two variables or three variables, we write xy or xyz, where x is, you can treat xy as x1, x2. So in that sense, the partial derivative with respect to x means it is fx1, in which case I have to write a tilde plus he1. And e1 is 0. Yeah, 1, 0. And e2 is 0, 1. So if you want to do the partial derivative with respect to x, you have to do h times 1, 0. And if you want to do the partial derivative with respect to y, you'll have to do 0.
Okay.
Right. So this is the limit as h goes to 0 of what is, this would just be f of h0 minus f of 0, 0. What is the given value of f of 0, 0?
0.
So this is 0 divided by h. And what is f of h comma 0?
Put in the equation that the other form.
Yes, the other form, but one of the coordinates is 0, which means that this will also be 0.
It will be 0,
So
yes.
yeah, so this is 0 minus 0 divided by h, and limit as h goes to 0 doesn't matter because it is identically zero. This quantity entirely is just equal to zero. So the limit will also be equal to zero, right? And similarly, you can check that fy at 0, 0 is equal to 0. What is fx at xy and fy at xy? We can do the same thing. We can go through all these computations, but in this case, we'll not have the comfort of having f of this part to be 0 in the corresponding part over there. So I'll postpone this to a bit later where there is another trick, not trick, but it's just a convenient way of computing. It probably comes right now. Yeah. So the partial derivative of a function can be computed by calculating the limit. That is the first principles way of doing. So if you have any function, you can just set up that limit, set up that quantity, try to analyze its behavior as h goes to 0, and then the limit will be the partial derivative. If the function is nice enough, by nice enough, I mean it is defined in a neighborhood in a same way using a closed form expression. So here you see at 0 it's defined differently and in a neighborhood it's defined differently. But for any other point, you'll see that there will be a small enough ball around that point in which it is defined the same way. So that is what I mean by nice enough. Such different behavior does not happen. It's not like a piecewise function or something. Okay. So such a thing, in that case, what you can do is you can just compute the partial derivative by differentiating it as a one variable function with respect to xi. What do I mean by that? As an example, let's take something simpler. Then I'll go back to that thing. Let's take just x squared plus y squared or something. Or maybe that's too. We always do x squared plus y squared. Let's do something like, okay, fine, e to the power x squared plus y squared. Now, if I want to calculate what is fx at, let's say, 1, 1, I could do the limit thing. But instead, I could also do fx at xy is I differentiate this expression as if y is a constant. So if y were to be a constant, if it is something like x squared plus 1, how would you differentiate with respect to x? This would just be e to the x squared plus 1 times 2x, right? So similarly, you think that y square is a constant. So you do e to the x squared plus y square times differential of, or dou by dou x of x squared plus y square. Now, what is differential of x squared plus y square? That is just 2x again, because
2x.
y is treated as a constant. So it's just 2x times e to the x square plus y square. So this is fx at a general xy. If you want fx at 1, 1, this would just be equal to 2 times e square. Okay, so for well-behaved functions like polynomial functions and so on, you can just differentiate it. If when you're calculating the partial derivative with respect to x, you treat y as constant, and if you're taking the partial derivative with respect to y, then you treat x as constant. So since you're measuring the change in only one variable, you're thinking of the other thing as constant. That's how you have to think about it. And there's a raised hand.
Sir, I have one question. Oh, you can go
Yes.
ahead with that, him also. So my question was this, that, for example, when you say that we have this well-defined enough, so it is nice enough.
Nice enough, yeah.
Sorry, nice enough. So every time
Yeah.
if you are given, let's say, some three piecewise function, for example, in the last it was undefined at 0, 0. For
Yes.
the example sake, I'm saying that let's say it is also undefined at 1, 2. It is completely hypothetical. I just want to make a point. That's why I'm saying. So if
Okay, so it is defined some way. So by the way, it's not undefined at 0, 0. It is defined as 0.
Yeah,
I mean,
yeah, it is.
separately.
Yes, separately defined.
Yeah.
So let's say it is separately defined at two such points. If we remove those 2 points, then we can consider this nice enough, no? Like,
yes, because in every other point there is a small ball such that the function is homogeneously defined. As in, all of these things are not. I mean, this nice enough is also I've not well defined, properly defined what it is, but that is the thing. Yeah, if you remove those 2 points.
In previous example, if we remove at 0, 0, then it is well defined.
and
Yeah,
this
it
we
is
can
nice
do with
enough outside
any,
of 0, 0. Yeah.
Yes.
if it is not given that it behaves very badly at some points, because it
Yes.
is multivariable, we can't even imagine it. So we have to
Yes,
consider,
yes.
we will consider it nice enough.
Yes, yes. If it is given by a single, rational expression of polynomials, trigonometric functions, and so on, that you can consider as nice enough.
Okay.
Yeah. So coming back to this problem, if I want to compute fx at x comma y at any point other than the origin, as specified, it behaves well in a neighborhood of or in an open ball around any such. So for this, I just need to differentiate this as if it were as if y were constant, and then I can use the usual quotient rule of differentiation, and I'll get x square plus y square the whole square, x square plus y square. So y is a constant, right? So it comes outside. So I just have to differentiate x minus x times 2x. Is this fine? Does everyone understand what happened here?
Yes, sir.
Yes.
Yes.
So this is the nature of the derivative or partial derivative outside 0, 0. And at 0, 0, you cannot do this. You cannot just say that I'll differentiate this and take the limit perhaps, or all these things don't work. For points in which the behavior is not so good, you have to use the limit table. So the practical way of computing limits is, computing the partial derivative is do just usual differentiation with keeping every other constant. So this is, here I've just said that when you're differentiating with respect to x, you keep y as constant. But if you have more variables, when you're differentiating or when you're calculating the partial derivative with respect to some variable, you treat everything else as constant. So you are measuring the change only with respect to one variable. So everything else is constant. So that's that. And yeah, if the function is not well behaved, then you have to do the limit process. Now, those were two directions. So when you look at a point, say in two variables, if your domain is R2 or some subset of R2, what we have seen is how the function changes in this direction and how the function changes in this direction. So when I take the change in input only in these two directions, so I just get the idea of the rate of change of the function along these two directions or the coordinate directions. So what about the other directions? For that, the concept is the same. You just look at a unit vector over unit vector in the direction. So I want to know how the function behaves, say in the direction of 1, 1. Then I should not use 1, 1. I should use 1 by root 2, 1 by root 2, because I need a unit direction. And in the instructor session, I think I had said incorrectly that you can use non-unit vectors, but yeah, take note of this thing. That is wrong. What I said earlier is wrong. You necessarily need a unit vector over here, because this would be if I don't take a unit vector, then it will be it won't be change in output divided by change in input. So I do need a unit vector. So instead of a tilde plus h times a coordinate direction, which is 1 0 or 1 0 0 1 0 1 0 0 0 1 in R3 or any of the standard basis vectors, instead of this, you change it to the direction vector. So you're changing the function in the direction of u tilde, and then measuring the rate of change, taking the limit the usual basis. Once again, the limit may exist, may not exist. And we'll take the same example for xy divided by x square plus y square and see if directional derivatives exist. Right. So we have seen that partial derivatives exist. And by the way, there is one remark over here that if u tilde is equal to 1, 0, I can take any unit vector, right? 1, 0 is also a unit vector. So then what would fu at a tilde be? Let's say we have a 2-variable function and I take the unit direction to be 1, 0. What happens if I substitute 1, 0 over here?
H comma 0.
So this becomes partial derivative with respect to x.
Yes, sir. Y is constant.
Just by definition, that's clear, right? Because if I put u tilde equal to E1 or EI in general, I'll recover back the definition of the ith partial derivative. So partial derivatives are directional derivatives in the coordinate direction. So coming back to the example, fxy is xy divided by x square plus y square, not at the origin, xy at the origin, I mean 0 at the origin. We saw that fx of 0, 0, that is the partial derivative at 0, 0, is equal to this is equal to 0. That limit, the quantity of which we had to calculate the limit itself was identically 0. But what about general u1, u2? Sorry. This is not our variable. This u1, u2, the directional derivative of f in the direction of u1, u2 at the point 0, 0. So what do? I look at the function at the given point, change the input value by h times the unit direction vector. Assume that u1, u2 is a unit direction vector. And then I subtract the initial value, that is 0, 0 in this case, f of 0, 0 in this case, and divide by h. And then I take the limit of this. Right. So this is like point plus change, function value of point plus change divided by function value at the point divided by the change. So that's how you have to, just a moment. Yeah. This is point plus change minus the function value at the point divided by the change. Now for a general u1, u2, this would be f of hu1, hu2 minus f of 0, 0 is 0, 0 as before. But what would this be? This would be h square u1, u2. I'm just substituting h1, hu1, hu2 in this expression. So I'll also get something like h square times u1 square plus u2 square times nh. So this h comes from the denominator of the limit expression, and then the others are just substitution of hu1 and hu2 for x and y in the definition. So you know that u1 square plus u2 square, this is 1 because I'm taking a unit vector. H square gets cancelled, and what I'm left with is u1, u2 divided by h. Now, what is the nature of u1, u2 divided by h? u1 and u2 are some constants. It's a constant direction vector. It is not some function of h. So this is nothing but u1, u2 times limit as h goes to 0 Well, this I should not write because yeah, that I can do only if the limit exists. So uh, strictly speaking, I should not do that. So the thing that I have to analyze is u1, u2 divided by h. What is the nature of u1, u2 divided by h as h goes to 0?
It goes to
It's like
infinity.
constant divided by 0.
So it blows up as we approach 0, or it goes to infinity. But there is a catch that if u1 and u2 were itself 0, that can happen, right? What is the case when u1 is equal to 0? This is your unit vector is given by 0, comma 1. Or if u2 is equal to 0, where the unit vector is given by 1, comma 0. In these two cases, the numerator being 0 makes this quantity u1, u2 by h itself 0. So that limit actually exists. Correct?
Sir, could you
Yes.
please explain the step h squared u1, u2, and then proceed with the next step? I couldn't.
So this I've just substituted hu1, u2 over here. So this becomes hu1, hu2 divided by h square u1 square plus h square u2 square. Sorry. Right?
Then how the
So this
u1 and u2 become
Sir, is it U1 and U2 are vectors, orthogonal vectors?
no, u1 and u2 are real numbers. U is equal to u1, u2 is the direction along which I'm taking the directional derivative.
Real numbers. So it must be 0. Any one of them is 0. Otherwise,
If anyone wait, let me first address this thing. Did you understand what happened over here?
yes, sir.
Sir, when u1 and u2 like a product of 0, like u1 u2 is equal to 0, and then it
Just a
did
minute, just a little bit. Yeah. Sorry.
what I'm saying, like if u1 and u2 and the
Yes.
dot product of this is going to be 0, right? So 0 by 0 form.
Dot product of what?
No, u1 and u2. Let's say u1 is equal to 0 and u2 is equal to 1 something, right?
Yeah, if u1 is equal to 0, then u2 has to be 1 because we have unit vectors.
Excuse me, sir. Instead of
Or minus 1.
Hy, you are taking HU1 and HU2 are the points, sir.
Yes. That's what we need to do, right? We have to do f of
It
0,
is a
0 plus
central
h.
point, HU1, HU2.
Yes.
It is moving in the direction of U1, U2.
Yes.
Okay. Okay, sir. Thank you.
I substituted hu1, hu2, and then I simplified the expression to this thing. So is this simplification part clear
Yes, sir.
for everyone?
Yes, sir.
Yes,
Yes,
yes.
sir.
Yes, sir.
Yeah. Now to analyze whether the limit exists or not, if u1 is equal to 0, this entire quantity is always 0, right? Irrespective of the value of h. So that will tend to 0 itself as h goes to 0. But if u1 and u2 were non-zero constants, then that thing blows up. Blows up meaning it becomes arbitrarily large as we approach 0. So the only cases where this limit exists is if u1 is equal to 0 or if u2 is equal to 0. Now u1 is equal to 0 corresponds to the y partial derivative, and u2 is equal to 0 corresponds to u is equal to 1 comma 0 or minus 1 comma 0, but we'll just take 1 comma 0. In any case, it is just the x partial derivative. So the conclusion after all this is that fx and fy exist. Fu does not exist for any other u. Any other meaning if they are not the coordinate directions.
Sorry, sir, but I didn't get it. Why you say when u1 is equal to 0, the limit should exist? Like it's 0 by 0 form now.
It's
No,
not a
the
0 by
entire
0
thing is zero
form.
there.
So
It
you
can
are
be
analyzing this function. Okay, so you are analyzing this function. Let us forget about the limit. Let us take this as a function of h. When you're taking the limit, you are looking at this function outside the point of convergence. Outside h is equal to 0, you're looking at this thing. Now u1 and u2 was a constant that you took in the first place. If the vector that you took in the first place was 1, 0, for example, what is this quantity equal to? This is just 0. This is not 0 by 0. This is the 0 by h, which is 0.
Yes, sir. Okay.
Right. So when you take the limit as h goes to 0, that will become 0. That is,
Okay.
this is a constant function. But if it is not, but if it is, if u1 and u2 both are non-zero, in that case, this u1, u2 by h. So let's take, for example, 1 by root 2, 1 by root 2 or something. 1 by root 2, 1 by root 2 is a unit vector. This is just an example that I'm taking. This function would become 1 by 2h, right?
Okay.
We are trying to get the limit of 1 by 2h as h goes to 0. Now this would be infinity, or the limit does not exist is what he's saying.
Okay, sir.
Right. So strictly speaking, when you're evaluating limits and so on, you should not write limit of this thing before you know that it exists. You just have to write the thing that you have to take the limit of, and then you have to argue whether or not the limit exists. Only if the limit exists can you write limit of that thing. But yeah, let's not get into the pedantic details of all of that. Now the next thing we'll see is limits of sequences. For real number sequences, you have an idea of what limit is. If I take 1 by n, for example, this converges to, as n goes to infinity,
0.
and there are, so take for example sine n. If, what about sine n?
Doesn't converge.
It doesn't converge because it keeps oscillating. So you know that it has to go in closer and closer to a point. There is a rigorous mathematical formulation of that, but that is not covered in the course and that is not required. You understand at least what it means for a real number sequence to converge to a real number. So in the same spirit, we just generalize it to sequences of vectors. So vectors in Rm. So a sequence of vectors in Rm, they are given by m real numbers. So for every n, you have m real numbers. So probably better to explain with a, let us take this.
Sorry to interrupt, sir, but at the
Yeah,
end, can you just share this PPT slide with us, like in the chat? Or
this will be posted in the same folder as usual.
actually, I don't have the access to that. I requested the access, but
Oh, okay. Let's discuss that at the end. You should,
yeah, sure, sure.
everyone with an ID should have access to that. But yeah, let me just verify that later. Yeah,
Actually, it has to be
because
approved. You have to request and then it has to be approved.
okay, I'll see. I'll see.
Sure.
Yeah. Now this is a sequence in R2, right? At every n, you have two real numbers. So this is what it means to be a sequence in R2. More generally in Rm, a sequence means at every positive integer, you have a vector in Rm or a set of m real numbers. Now, what does it mean for a sequence to converge, a sequence of vectors to converge? Each of the components have to converge. Even if one of them does not, then it is not a convergent sequence. Take, for example, 1 by n e to the minus. Does this converge?
No,
As n? Yes or no?
Yes.
Yes, sir. Yes.
What does it converge to?
0, 0.
Zero. Zero, zero,
Right. Let's say 1 by n e to the n.
no, sir, it is not
Does this?
0, comma.
infinity.
But that's infinity is not a real number, so this does not converge, or it diverges.
Yes, sir.
So even if one component does not converge, then the sequence is said to diverge. All right. Okay. Next, we'll take a look at limit of a scalar valued multivariable function. Scalar valued limits of one variable functions is known, right? There is a raised hand.
Actually,
Is
sir,
there a doubt?
like when you say converging, right? So it does mean like only we can converge towards zero or something. Let's say any point.
It can converge to anything. You can just add, let's say, 1 plus this thing. And this would converge to 0, 1.
And let's say both are different. Let's say both have like different convergence. Then
That's also okay. You can have 2 plus 1 by n and you can converge to 2, 1.
okay, okay.
So you just do the same analysis that you know point-wise is all. You look at
Okay.
the first point, you get a sequence. If that converges, the limiting point has that as the first coordinate. Then you look at the second point, take its limit. Its limit would be the second coordinate of the limit vector. So real number sequences have a real number as a limit. So a vector sequence will have a vector as a limit, for which each component is given by the limit of the corresponding sequence of, say, ith component. The ith component of the limit would be the limit of the sequence given by the ith component of each of the sequence. Is that
Okay.
okay?
Yes,
Yes,
yes.
sir.
So next, we look at scalar valued function defined on domains, the limit. In one variable, you know that if you have a function, if you want to check continuity at this point, the domain is a line. The domain is a line, meaning you can approach this. If I'm checking the continuity at the x mark point in the diagram, there is really only one direction that I have to look at. Well, two directions. One is the negative of the other. So this is why you have this right-handed limit, left-handed limit. So there's this notion of if the right-handed limit is equal to the left-hand limit. So is that issue resolved? Do you have can you see the folder? Just a moment. I just clarify with the.
Yes, yes, yes. Someone just provided. Thank you.
Yeah. So that does not require any access, right? I mean, that does not require any permissions.
Yeah, I confused it because in Google Meet there was another link that actually is
Okay.
required.
Okay.
Sorry
Alright.
to interrupt, Akash.
Yeah, no problem. So here, in a one variable case, you have only really one direction to vary about. So you just look at right-hand limit, left-hand limit. If both are equal, then you say the limit exists. Or in the case of infinity, it's a little different, but that's not relevant over here. But in the case of, say, a two-variable function, you know that the graph looks like something like this. Let's say your xy plane is the domain and your z is the codomain, or the function value is given by z is equal to f of xy. For any point on the domain, there are multiple ways to approach that point, right? There's infinitely many directions along which you can approach that point. So when we talk about limiting value, what we have to make sure is that along each of those directions, the limit is the same. So it's no longer just left-hand limit, right-hand limit. It is any direction limit, so to speak. and any direction in any possible fashion. So the formal way of doing that is to say that given a point on the domain, or given a point not necessarily on the domain also, like this a tilde could not even be on the domain. As long as I have a path to it through domain, if I consider a sequence of points, yeah, if I consider a sequence of points which converge to this point, then I look at the function values at each of these points. The value that those function points tend to, they have to be the same across all sequences. Once again, this will be made clear with an example. But the idea is that irrespective of what sequence that you take to converge to your input vector, the function value of the corresponding sequence. So if an goes to an tilde, because these are vectors, right? So let's just call them an tilde and a tilde. Irrespective of what sequence an tilde you take, which converges to a tilde, you need that f of an tilde has to be the same. F of an tilde has to go to a single vector L. If such a thing happens, then L is said to be the limit of f as you approach a tilde. Maybe this will come later. Let's take this thing. Is this function continuous? I'll go back to that slide. That slide is also important. But before that, let's just take the same function. We are doing analysis on the same function. This is just a model, and the numbers are different. The function is different. The analysis, or at least the way of analysis, is the same. So is this function continuous? So to say that it is continuous, what do I need? Irrespective of
Limit, right hand limit, and
Limit should exist.
so yeah, so this is what I'm saying. So if for a multivariable function, there's no right hand limit, left hand limit, because what is your domain? Your domain is the xy plane, and you're looking for continuity at 0, 0. So all of these things, the whole plane is your domain. So it's not like there's any left hand limit, right hand limit. There's more also. So what I have to see is the function behavior with respect to anything that converges to the point. More precisely, if I have a sequence xn, yn of points which converges to 0, 0, then f of xn, yn is what I'm worried about. F of xn, yn, I have to analyze the behavior of f of xn, y. Yeah, you don't need to raise the hand and wait for me to, you can just ask the doubt.
Sir, my doubt was then in such a situation we can approach this point in any direction. Like you can take any function. Then for how many functions are we supposed to check this limit?
Right. That's a good question. I'll address that question a bit later. So for this particular example, let's see how it works. So if you look at xn, yn along, so once again, let me just draw this domain. The domain is this, the point of interest is 0, 0. If I travel along this line, for example, which is, let me call it 1 by n, 0. Right? As I increase n, I go closer and closer to 0. What is f of x and yn? Or what is f of 1 by n, 0? What is f of n, 1 by n, 0? That should not be
0.
That's just 0, right? So on this line, which is the x-axis, the function is identically 0. Correct? Similarly, if xn, yn is just 0, 1 by n, by which I mean I'm traveling in this direction, even then f of xn, yn is 0. because the numerator becomes 0, correct? But what if xn yn is equal to 1 by n 1 by n? Then what is f of x and y?
Finite.
What is it?
1 by 2.
1 by 2.
Yeah, this will be half, right? So along different sequences, x and yn, which goes to 0. So what is 1 by n 1 by n? I'm just going like this, correct? Which is along the line x is equal to y.
Yes.
So if you want, you can take another. This is enough to say that this limit does not exist. But let me take 1 by n, comma c by n. I could take a better constant so that everything simplifies. But this will be some c divided by 1 plus c square.
Yes, sir.
And I can modify the c to get any possible limit as the limiting value of the function along the sequence. Correct. So along different lines, in this case, along different lines, you get different limits for the function. So f
Sir, excuse
limit
me,
of
sir.
f does not exist.
Sir, excuse me.
Just a moment. Limit, I've not written it out fully. Limit as xy goes to 0 of f of xy does not exist. Because along different curves, the real thing is to consider all possible curves. Alternatively, you can take sequences and work with them. Yeah, what was the doubt?
Sir, how the 1 by n f of x and yn becomes 1 by 2?
Which part did you not understand? So
The
this
last
was
but one
first,
before
2, 3,
third,
4.
third and
The third one is I consider the sequence x and yn is 1 by n, 1 by n. So what is 1 by n, 1 by n? This lies on the line y is equal to x, right? On your domain, the line y is equal to x is just this. And I'm moving towards the origin along this line, correct?
yes, then now it
And
becomes 1 by 2.
so f of x and yn is just f of 1 by n, 1 by n. If I substitute 1 by n, 1 by n over here, it becomes 1 by n times 1 by n divided by 1 by n square plus 1 by n square, which is 1 by n square by 2 by n square, which is just half.
Oh, okay, substituting function. Okay, sir.
Yeah, because 1 by n, 1 by n is not 0, 0. So I can use that other definition and then just substitute it to get half.
Okay.
So if you look at the function along this line x is equal to y, you will see that the function is always half, but suddenly at 0, it crashes down to 0, which means it is not continuous. So in the one variable case, for example, when do you say that something is not continuous? When you have something like this, a jump at some point and then this, right? So, or if your left hand limit is not equal to right hand limit, for example, then you say that it is discontinuous.
It's discontinuous.
So, for multivariable functions, what happens is this happens in possibly many directions. So you have to take all possible sequences that tend to the point, and the corresponding function values, they have to go to the same point, same vector. Only in that case, the limit exists.
Sir, how we
But
can
now
say in the third point, we can say that it's checking along the y equal to x line.
well, it's a part of the y is equal to x line, but it is close enough to 0. So even if you substitute y is equal to x and look at f of x comma x, then you'll get what I'm trying to say. But
Yes,
here what we are doing is this x and y n, where are these points? This 1 by n lies on the line y is equal to x, right?
since it's tending to 0.
and it is tending to 0. So it's like on the domain, you have this point 0, 0, and you're taking closer and closer points.
Okay, okay. That's why you are telling that.
Yeah, I'm going towards the origin along a converging sequence of vectors which lie on the line y is equal to x.
Okay, okay. Got
All
it.
right. Yeah.
In the first, we are going along the x-axis and second y-axis.
Yes.
Okay.
And third one is y is equal to x, and the fourth one is what? X is equal to no, y is equal to cx. So this is like y is equal to mx.
Okay.
Sir,
So that is another line through the origin. Yeah.
in fourth option, we can conclude like if entire our limit is in form of something C, right? So it
Yeah,
definitely
that
then
c
will.
was some arbitrary, but it is constant, assumed to be constant. So take it to 2 or 3 or whatever you want, whatever you want it to
That
be.
means our entire limit is depending on C, right? So it does not exist because we
Yes.
can take value.
Yeah, that was clear over here itself, right? So there is along one line you have 0, and along another line you have half.
Okay, okay.
So that limit does not exist. But here it is, as you pointed out, even more so, because depending on the value of c, I could get any possible limit,
Sir,
because this function in C is probably surjective. You know, I'm not sure, but yeah, it looks like it. Yeah.
I have one question here. Like,
Yes.
so since we are taking some y equal to mx type of thing,
Mm-hmm.
it covers all the direction.
It covers all the linear directions, yes, but that is actually a good place to exercise caution. Even if you get that the limit is the same along every straight line, that is not enough. That is why you have every possible sequence over here. So there are functions for which the limit along every line is the same, but then along some curve it is different. So if you take all possible curves, then you're good. But taking all what is all possible curves? How will you check along all possible curves? That does not make sense, right? So here, this is where there is another definition. But for the context of this course and the problems that you will be getting, you will be
So,
able to
so,
either you
so
will
we will
be
check
able to
for
get a easy curve. Sorry.
okay. So we will check till that curve which we will get different limits.
Yes. So if you want to prove that the limit does not exist, all you need to produce is one curve, I mean two curves along which the limits are different.
Okay.
But if you want to prove that the limit does exist, it is harder, because what is it asking? It is asking you to either say that the limit along every curve is the same. I mean, every curve means like there are uncountably infinitely many curves. So that's
Yes.
not an easy problem.
Um,
Or
for
it's
that,
it's saying that or alternatively you could take any possible sequence which converges to A and look at the function value. That is also not easy. So that is where these comments come. So especially the last thing, which is sandwich principle. So if you have to prove that something does have a limit, then sandwich principle is your friend. And the problems that you will be asked for this course, if the limit exists, you can prove it by sandwich principle. Or some just using sum of limits is, so if you take something like x square plus y square as xy goes to 0, 0. This is very, very primitive example, but here x square goes to 0 as xy goes to 0, 0. So y square goes to 0, 0. So the sum of the limit is the limit of the sum. Scalar multiples don't change anything. Now, the only problem comes where when you have things like 1 by x square plus y square and things which above also. If you have things like this, then it's a problem. And all such things, the functions that you will be asked to analyze, you will be able to solve using sandwich principle. The rigorous way to do it would be something else, the epsilon delta definition and so on. So that is not that is nowhere in the
But
course.
even if we
Yes.
consider something like I have read somewhere like they do something like they take some curve and then they restrict the function to that arbitrary curve and they do some kind of parameterization. Is that
That you
any
can do, but what are all possible curves? Like take for example 0, 0 itself. Y is equal to x to the n. All of these things are, I mean, x to the n for arbitrary n. Each of these is a curve that passes through the origin. You can take m to the n. You can vary m. You can vary n. Each of them passes through the origin, and these are like still polynomial ones. There are things like say sine x and 1 minus cos x. You could like the space of curves to a point is huge, whatever huge means. So you cannot sit and verify for each possible curve this thing happens. That is not a reasonable thing to do. Do you get that at least?
Okay, yes,
As
I
in,
get.
in principle, I'm not giving you a very robust argument because yeah, then we'll go way off the
No, I get
course
why it is
content.
difficult. I get why it is
Yeah,
difficult.
you get that, right? Yeah, that's what I'm trying to say. So verifying for each, and I think that is what Shivam also was asking about.
Yeah, yeah.
And yeah, so if you, well, to prove that it is the limit exists, you need sandwich principle, and to prove that the limit does not exist, you need just two curves. Most of the times lines. If not lines, then some polynomial functions. You can verify that this limit like limit along two lines or two curves is different, then you can say that the limit does not exist. To give you an idea of that point, I actually have written up this example. Now, I'm given a function which is defined everywhere other than at the origin. What is the limit as xy goes to 0, 0 of this function? Now, once again, it looks like something that blows up at the origin, right? There's some factor which becomes large as I go closer and closer to the origin. So let us take the line y is equal to mx. So f of x comma mx. What does this look like? This is x minus mx the whole square divided by square root of x square plus m square x square. This is some m square divided by square root of 1 plus m square times 1 minus, no, what am I doing? No, this is wrong. This is 1 minus m the whole square by x square divided by x. This is correct, right? I've just substituted y is equal to mx and simplified. This is fine.
Yes, right.
Yes, sir.
Yes.
Yeah. So the limit of this thing is 0 as x goes to 0. So when I'm saying xy goes to 0, it means x comma mx goes to 0. So this thing goes to 0 irrespective of the sign of x, because above you have something dominated by x square that you can verify that this goes to 0. So along every straight line, this thing is going to 0. So how do we go about analyzing this? So as it turns out, this function does have a limit. And to find the limit, we use sandwich theorem. So look at this quantity x minus y the whole square divided by square root of.
So we have checked along straight line only.
We have checked along straight line only, and we have got the limit to be the same. Now that does not mean that the limit exists, but now what arbitrary curve can you take? Or if you, so let us,
Y equal to
so
x square.
You can try that. I'm going to tell you that everything will give you the limit is 0 because this limit actually exists. And I'm trying, this part is the proof of why the limit exists.
Okay, sir.
All right. So this divided by square root of x squared plus y squared. Now this quantity is square root of x squared plus y squared minus 2xy divided by square root of x squared plus y squared. Now when you have things like 2xy by x squared plus y squared, so then one more practical suggestion is that when you have things like sine or cos, if you want to use the sandwich principle, you say that sine is restricted between -1 and 1 and then analyze. And when you have things like this, you can use the AMGM inequality, or well, here you don't even need the AMGM inequality. So let's keep this out aside for now. Look at this thing. X squared plus y squared is greater than or equal to 2x squared. Do you know why?
Yeah, the whole square is all
Yeah,
so
x minus y the whole square is uh,
It's quite obvious.
real.
yeah, it's non-negative. So if I bring one of the square root of x square plus y square is down, so you will just get that this square root of x square plus y square right? Or since I'm dealing with minus 2xy, let me just write this as this. This is okay. And on the other hand, I have x square plus y square is also greater than or equal to minus 2xy. Why? Once again, because x plus y the whole square is greater than or equal to 0. So what does this give me? This gives me square root of x square plus y square is greater than or equal to minus 2xy divided by square root of x square plus y square. So using this, I can sandwich minus 2xy divided by x square plus y square in between minus x square plus y square and plus x square plus y square, square root of, correct? So all of this leads to minus square root of x square plus y square is less than or equal to minus 2xy divided by square root of x square plus y square less than or equal to 2x, or what is it? Square root of x. So now if I add square root of x square plus y square throughout, which is a positive number, I mean, adding is fine anyway, I get that 0 is less than or equal to square root of x square plus y square minus 2xy divided by square root of x square plus y square is less than or equal to 2 times square root of x square plus y square. Is this clear?
Yes, sir.
Now can we use sandwich principle? This part goes to 0 as I go to 0, 0, just directly by substitution. This part is identically 0. So if there is a function which is sandwiched between two functions, both of which go to a particular number as I go towards the candidate number, as in this case, as xy goes to 0, 0, both my left hand side and right hand side, right, lower bound and upper bound, both of them go to the same value 0. So the function in between also has to go to the same limit. That is the sandwich principle, which says that this limit of this function as xy goes to 0, 0 is 0. But that was my function f of xy, right?
Yes, sir.
Is this clear to everyone? Why f of xy does have a limit and it is equal to 0. This is a slightly more involved example. Most of the time, you will just be dealing with having to use the property of sine and so on. And there will be easy curves to check. But I'm just saying that whenever you have a square root of x square plus y square, you can use this just the property of x plus y the whole square is greater than or equal to 0, x minus y the whole square is greater than or equal to 0, and so on. These things can give you nice arguments as to why limits of certain functions exist. So this part is clear, right? Like how we use the sandwich theorem to conclude that the limit of fxy is for everyone. Is it clear?
Yes, sir, it is.
Yes, sir.
Yes.
There is no one-shot algorithm to just look at a function and say whether the limit exists or not. It's a little bit of a trial and error. You check with known, straight lines, x square, exponential. The usual function, the polynomial function. And if it is not, maybe then the limit does exist. If the limit does not exist, for the questions that we generally ask, it is the curve along which you have to check will be clear. So that's about it. As in, I cannot tell you that you look at this thing and how will you know whether the limit exists or not. That there is no complete answer.
Excuse me, sir.
Yeah.
So could you briefly tell us all the steps, general steps that we could take to approach these types of questions?
Yeah, so this is probably what I'm discussing next. So first of all, substitution. If substitution gives you an answer, then that is the limit. Now, in case where substitution fails, which means you have some denominator equal to 0 kind of behavior near the point of interest, then to establish non-existence of limit, you need an appropriate sequence or two sequences which converge to different points, or one sequence along which the thing does not converge at all. And to prove the existence, you need to use the properties of limits. Properties of limits being the sum scalar product, all of these properties along with sandwich principle. And yeah, even with sandwich principle, there is no, this is the function that you have to use every time. So these are some checklists that you can go through, but there is no short way of saying that this is how you establish or not establish that the limit exists. So you have to do a little bit of trial and error, but I can almost ensure that the problems that you will be asked for will be simple in the sense that the path will be clear as when you see.
So looking at the partial derivative existence for any function, can we comment on its continuity at that point?
No. Take, for example, this the function that we had discussed itself. The partial derivatives do exist, but the function is not continuous. The partial derivatives exist, but the directional derivative does not exist. Any other directional derivative does not exist, but this is not a continuous function. So if all the directional derivatives exist, maybe, but that would be a harder check than this. Even if, yeah, I cannot think of an example off the top of my head, but if all directional derivatives exist, also the function may be discontinuous.
Do we have to check the differentiability of the function at that point?
Well, differentiability implies continuity is correct, but differentiability is harder to check. I mean, yeah, in general, it would not be that easy to check.
Then what does this partial derivative exactly tell us at that point?
It just tells you the nature of the function when restricted to certain lines. So if your domain, let's say, is R2 or some part of R2, partial derivative says, so the graph of the function is something that looks like this. So the xy plane is the input and the z is the output as usual. So it's some surface like this. Above each point, you have the height to be equal to the function value at that point. Now, if I look at this point and look at the partial derivative with respect to x, I'm just looking at the part of the graph which lies above this point, which is something like this. Now, if the partial derivatives exist, that does not imply that it is continuous, right? It along some other direction, there could be a break. The break can happen in arbitrary direction, but the partial derivative only is concerned about two specific directions. Along those two specific directions, the graph may be smooth.
Okay, I got it. What you're trying to say.
Yeah. Yeah.
Take the edge of a box along the line, it is kind of continuous. But if you just
Yeah, well, the question was not about continuous and not differentiable function, but what is the, I mean, how do you visualize probably partial derivatives, or why do partial derivatives not imply continuity is what I think he was asking about. So partial derivatives is concerns restrictions of multivariable functions in certain directions.
And for continuity, we have to consider all directions.
Yes, and all directions, not just linear. It is even along some curve. It could be a problem, right? So this function, which is x square, or maybe it was xy square divided by x square plus y4. I think this you can check that along y is equal to mx, you will get m square x square divided by m. This is this what I want? Probably not. X is equal. Let me do this. X square y x square. Yeah. If I take this function, if I put y is equal to mx, I get m x to the power 4 by x4. Okay, I don't remember the exact example, but there are functions for which every line there is continuity, but there are specific curves along which there is no continuity. You can Google this and you'll get it. Okay. So yeah, those concern specific lines, but this continuity thing concerns the entire behavior of the function in a neighborhood, which includes arbitrary curves as well. So differentiability is a stronger requirement, but it is not probably an easier check. Differentiability is not existence of directional derivatives. It is something that we'll see later. Okay. So we have already in disguise said what continuity of a scalar valued function is, but this is the formal definition. If the limit at a point exists and is equal to the function value, then such a thing is called continuous. Once again, whenever there is doubt as to how to think about it, you look at the one variable case. If left hand limit is equal to right hand limit, then you say the limit exists. But if that limit is actually equal to the function value, then you say that the function is continuous. Similarly, for multivariable scalar valued multivariable functions, if the limit along every sequence, or alternatively along every possible curve, is equal, then you say that the limit exists. And if it is actually equal to the function value, then you say that the function is continuous. Continuity of partial derivatives of this. Okay. Let's see, partial derivatives are also, again, multivariable functions. So I'm not concerned in this example, I'm not concerned about the continuity of f. I'm worried about the continuity of the partial derivatives of. So let's first compute what the partial derivatives of f is. This we have already done. F of x, let's say xy. This is equal to 0 at 0, 0. But for xy not equal to 0, 0, we computed that this was y times something like x square plus y square minus, what would it have been? 2x square, I think.
Yes, 2x square y.
This should be the expression. So outside 0, 0, I'm just going to differentiate it, treating y as constant. And then at 0, we found that the partial derivative is actually equal to 0, exists and is equal to 0. Now, what is the what can we say about the continuity of this function? Is it continuous?
Not, sir.
So do you know any curve along which it is not going to converge? So this is what? Y times y square minus x square. So it's like y cube minus x square y divided by x square plus y square, the whole square. So I'm just rewriting the function definition. So let's see y is equal to mx. You will have m cube x cube minus x square mx divided by x square plus m square x square the square. Right, this is f of x comma mx. I'm not writing it out separately. But here I'll have x cube times some function of m. It is, in this case, it is m cube minus m divided by the x square comes out and I get an x to the 4 times 1 plus m square whole square, right? So I'm left with 1 by x kind of a thing times a constant. Now if m is equal to, I don't know, if m cube is equal to m, which is 1 minus 1, 0, whatever those things are, y is equal to x, y is equal to minus x, and y is equal to 0. Along these lines, you will have this to converge. But if you take m is equal to, say, 2 or something, then it is easy to see that this does not have a limit. Correct? This is the function value along the line y is equal to mx. And along certain lines, say y is equal to 2x. This becomes arbitrarily large as I go closer and closer to 0. So the limit does not exist. So fx as a function is not continuous. Is that fine?
Yes.
Yes, sir.
We have seen that f is also not continuous. In this case, we also saw that fx is also not. So there is this result about differentiability. If it is too confusing, just ignore this. But just know that if the partial derivatives exist and are continuous in a neighborhood, then the function is differentiable. But this should not have happened here, because if the partial derivatives were continuous, then you would get it to be differentiable and then you would get the function to be continuous. But we already have seen that this function is not continuous. So this would have been reduced in other ways also, but those results are not discussed in the course. So just know this for your own understanding.
Is it true otherwise, sir? Suppose if f of xy is differentiable, then the partial derivative will be
Partial
continuous.
derivatives need not be continuous.
Okay.
So things like in one variable, you have these things, no? X square sine 1 by x, I believe. This would be differentiable, but the derivative is not continuous. You can have two-dimensional versions of these functions. Yeah. Next, we have the concept of gradient of a function. Gradient of a multivariable function is just the vector that is obtained by putting together all the partial derivatives. So, of course, then requirement is that the partial derivatives must exist. If the partial derivatives do exist, then this is called the gradient at that point. Now, the gradient, so in the case of partial derivatives, we saw that if there is a nice function, whatever that means, then you can just differentiate it as usual and get it, and you can circumvent this whole limit taking process, which is typically cumbersome. But what about directional derivatives? So the gradient actually gives you a way of computing directional derivatives without having to go through the hustle of taking the limits using the direction vector. And that is one of the applications of the gradient vector. But it is important to note that not only do you need the gradient to exist at that point, but it should also be continuous in a ball around that point. Now, if you take a look at this guy, so the gradient exists for this, right? Xy divided by x squared plus y squared. We saw that fx, fy exist, but none of the other direction vectors exist. And also we saw that the partial derivatives are not continuous, which means the gradient is not continuous. Gradient is just has this component functions as the partial derivatives, which are not continuous. So the gradient is not continuous in the neighborhood of 0 in that case. But for functions for which the gradient exists and is continuous, then the directional derivative exists and is equal to the dot product of the gradient with the direction vector. The direction vector, as usual, is a unit vector. So if I want to say take, let's say, e to the x square plus y square, I want the direction vector in the direction of 1 by root 2, 1 by root 2. Let's just take 1 by root 2, 1 by root 2 at the point 1, comma 0. So what is the gradient of f at an arbitrary point xy? This would be 2x e to the x square plus y square, comma 2y e to the x square plus y square. So the gradient at the point 1, comma 0 is equal to
2e about
2e. That's it, right? 2e, comma 0.
2e by root 2 side.
This is just the gradient I'm talking about.
Okay. Yeah, gradient.
So f 1 by root 2, 1 by root 2 at 1, comma 0 is equal to 2e, comma 0 dot with the direction. So here you need the unit direction vector that you have to be careful about. So this will just be e by root. Now you can verify using the limit definition also that this is true. It might be more difficult, but yeah, that you can take as an exercise and verify that this is true. But here we did all of these without verifying that the gradient exists and is continuous and so on, because here this is just composition of exponential, polynomial, sums of functions. These are all very well behaved in the sense that they are differentiable. I mean, the partial derivatives exist, they are continuous, they are infinitely differentiable, so to speak. Right. So, but in general, if you are going to use this, you have to verify that the gradient exists and is continuous. All right.
This will be root 2e.
No, 2e times 1 by root 2. Oh, right. Sorry. Yeah.
Rationalize.
Yeah. Correct. It's root 2. Well, check the result for fxy. This is what I was saying, that this result cannot be used. So if the result could be used, just using, if we ignore this thing, if if we ignore this part where is continuous, suppose gradient exists, then then the conclusion is that the directional derivative exists, but we know for this function that the directional derivative does not exist in any other direction. So the continuity of the partial derivatives is very, very important. So this is a common trap that you can uh, you can just use this result without verifying the continuity of the partial derivatives and you go wrong. Right? So another application of the gradient is to determine the rate of, determine the direction in which the function changes the fastest. So this I won't spend much time on because this is just remembering that in the direction of the gradient vector itself, that your function changes the most. Function increases the most, and in the negative of that direction is where the function decreases the most, and orthogonal to the gradient vector is where the function remains unchanged if there is a direction in which, and typically there will be because you will be in more than one dimension.
Sir, I have a question here.
Yes.
This orthogonal to u, so u is on the surface of f. U is some direction in the surface of f.
U is a direction vector, so it's not in the surface of f or anything. So if you have, say, a function like this, and you're looking at this point, and suppose and the corresponding point, this is x comma y, and I'm looking at this f of x comma y upstairs. The function value gives the height of that point. Now, if I see that the gradient vector will be what? It'll be this is a two variable function. This will just be fx comma fy at that point would be the gradient vector. Now, in the domain, if you look at it, it will be some vector like this in that direction. Or if you look at it, if you look at the corresponding thing over there, see, the directions that you're determining are on the domain. Because the change that is happening, so fu is change of f in the direction of u, which means that at this point, if I move in this direction, the corresponding values, how they move, that is what you're looking at. Right. If I move in the direction of the gradient vector itself, I can expect the rate of change to be maximum. However, if I move in a direction orthogonal to the gradient, the function value does not change. The corresponding function value. So this is in the xy plane. All of these vectors, this vector is also in the xy plane. Okay. So if I move in the domain in the direction orthogonal to the gradient vector, then the corresponding function value does not change, or at least infinitesimally does not change.
So when I move orthogonally to u, so this arrow.
When you move orthogonally to the gradient.
Okay.
What essentially the gradient is there in physical means?
Well, the gradient is the measure of change. That is what it means.
Sir, can you just briefly tell that in lecture, I think the professor introduced this thing like, so if you write the equation, if you do this dot product, it would give rise to some hyperplane in n-1 dimension, that he introduced this thing, which is very close to what we do in this tangent plane, which at least sounds very close. So can you just briefly?
I don't know what you're referring to. The hyperplane obtained by solving which equation? In any case, I think we'll take that up later because let me cover the content first, and then we'll.
Okay. So at the end, can you just briefly? I'm actually
sure.
At the end of the class, can you just give me an idea of the proof of this hyperplane, which I'm very confused about, and I don't want to waste the problem solving session there. So at the end, if you have some time.
Okay. Sure. I don't know if I remember the proof of that, but let's try to do it later.
Okay. I'll give you a knock at the
Yeah.
end.
Yeah. Okay.
Sir, can you give any example for that results? FU is positive and maximum if del of FU by modulus of yeah, any norm of any example for the that results?
So you can take any function that you like and you can check it. Uh, as long as the gradient does not vanish, you should be able to. So what do you mean? I mean, what do you want? Do you want an example of a function? And
Yes,
then,
yes,
so computing the gradient, we have already done for many functions. So I did not want to give examples for this in addition because it's just compute the gradient and normalize it, right? You can take
I
an
am
example
asking, is it
function as well.
u is equal to that norm function is coming? No, I want to see that u
So
is a part
you,
of what? U is part of that real part of that f. No,
okay,
yeah, that
let's say, no, u is just gradient of f at the given point divided by the norm of that, which makes it a unit vector. You are just taking the direction of the gradient vector and then uh, you are normalizing is all you're doing. Let's take up an example at the end if we have time. All right. You'll probably, once I give that example, I think it'll be clear, but there's quite a bit of ground to cover, so I'll go ahead. So the next thing is tangent lines and planes to the graph of multivariable functions. In higher dimensions, this is difficult to visualize, but at least in functions of two variables, it is easy to see. So if I have something like, say, a hemisphere, right? Suppose this is the graph of some function, at some appropriately defined function. At a given point, you know what it means to say the tangent plane at that point, right? Everything orthogonal to, I mean, the radial vector, but that's not how you interpret it. But given a surface in 3 space, you know that a plane that just grazes the surface, this is called the tangent plane. And any line in that plane is actually called a tangent line. So given, let's say, the hyperbola, right? At the bottom, the tangent plane is actually the plane which is parallel to the xy plane, right? And any line to that, any line which passes through that point and lies in the tangent plane, this is called a tangent line. The equation of such a tangent line, so given a point, I have many tangent lines. So you have to tell me what is the point and what is the direction. So if you have a point and a direction, then you can determine the tangent line at that point on the graph in that direction. So there is a point a tilde. Let's just call it a tilde, and direction. Let's say u tilde. Let's just call it u, which is u1, u2, or in more generally u1, u2, un. If I'm given a point on the domain a tilde, let's say some arbitrary surface. Now the corresponding point is over here, f of a tilde. This is f of a tilde comma f of a tilde. And if I'm giving you a direction u, then you can determine the tangent line through that point in that direction. How do you calculate that? So here you use the notion of, I mean, you don't use it exactly. You can just memorize this if you want. It is a comma f of a tilde comma f of a tilde plus t times u fu at a tilde. But this should be thought of as an affine subspace of dimension 1. What is an affine subspace of dimension 1? It's a translate of a linear subspace. What is a linear subspace of dimension 1? It is just scalar multiples of a fixed vector. So you look at this point. This point is actually a tilde comma f of a tilde, right? This is the point on the graph. So this is the particular point plus scalar times direction vector. Now the direction vector is given by u comma directional derivative at u. And this is how you have to imagine this. So this is point plus t times direction vector. Or this is point plus linear subspace, which is just an affine subspace. So if you have to describe an affine subspace, there are two things that you need. You require a point and a linear subspace. So translates of linear subspaces are affine subspaces. So lines in R3 in general are affine subspaces of dimension 1, and the linear subspaces of dimension 1 in R3 are lines. I mean the straight lines as we know them, which are given by scalar multiples of a fixed vector. So this direction guy determines the linear subspace which is given by u comma fu at a tilde. And then you take the scalar multiple of that. Now this gives you a linear subspace, and you translate that by a tilde f of a tilde. The set of all such points gives you the tangent line at that point in that direction. So the point that you are given will determine by what you have to translate, and the direction that you are given along with the directional derivative at using that direction gives you the linear subspace, the description of the linear subspace. So in this way, it is easier to memorize, at least for me, and you don't really need to memorize. So since it passes through the point a tilde f of a tilde, that is the point, and t times the direction vector you want, and the direction vector is given by the direction vector that is given in the question, and the third coordinate is just given by the directional derivative using that direction at that point. So once again, maybe at the end we'll take up some example. The next thing is the tangent plane. Now this thing required, the tangent line required a point and a direction, an a tilde and a u. But the tangent plane just requires an a tilde. Why? Because there is no particular direction, because you are looking at the whole plane, right? The way to see this is analogous to what you have in one-dimensional calculus. So if you have a function y is equal to f of x, what is the equation of the tangent line? Assume that it is passing through it, or let me try to make it pass through that. So suppose this guy is x comma f of x. What is the equation of this line?
Y minus y1 equal to?
Yeah, y minus y1, you have f of x, right?
Yeah. Equal to
is
m
equal to
m into
what
x.
is m?
Slope.
f dash x.
Yeah, m is slope, and slope is given by the derivative. So f prime x times x.
Minus
Well,
x.
let's call this x naught. So this is x naught f x naught, right? So you can write this as y is equal to f of x naught plus f prime x times x minus x naught. So the same thing appears over here, but now instead of f prime x, you have the gradient. The gradient is the equivalent of the derivative, and f of x naught has become f of a tilde, f prime has become the gradient, and you cannot multiply a vector with another vector in any other way than the inner product that you know. So this is the standard dot product over here, instead of just multiplying f prime x into x minus x naught. So this is how you have to see, and typically you will get some equation of a plane that is equal to some ax plus by plus some d. I mean, you can rearrange it more nicely, but yeah, what you will get is something of the form. But to remember this equation, it is always, you can keep this in mind. Y is equal to f of x naught plus f prime x times x minus x naught. This is a very well known or even derivable on the spot, as I would like to think. And you just use the corresponding notions which have been generalized in the higher dimensions to get the formula for the plane.
I could not.
Sorry?
The proof you're talking about, no?
And I'm not talking about the proof. I'm saying how to remember this and
Oh,
how to think of this. This is just the multivariable version of this formula. So this formula is fine, right?
yeah.
Yeah. And instead of the derivative is just a single number. Or you could think of it as a 1 cross 1 vector also in one dimension. Now you have a 1 cross 2 in case of R2 or 1 cross n in case of, or n cross 1, whichever way you want to think about it. And you have to take the dot product with the x minus a, and then you will get the entire plane. I'm not saying that this is the proof of the thing. Of course, this is not the proof, but this can be seen as a parallel to that. Instead of mindlessly memorizing the formula, you can think of it this way. So yeah, let's go ahead. Maybe we'll take one common problem for all of these things a little bit later. But in 10 minutes, we have to finish critical point. So once again, model space, one variable calculus. Critical points are points where the derivative does not exist or is equal to 0. It is also known, okay, fine. That maybe comes next. Generalizing to this, the parallel to derivatives is the gradient. So for a scalar valued multivariable function, if you have a point at which the gradient is not defined, does not exist, or if it exists and is equal to 0, these are two mutually exclusive cases. In these cases, it's called a critical point. Critical points are where the gradient vanishes if it exists, or if it does not exist, it is automatically a critical. Now, local extreme of scalar valued multivariable functions are critical points. The converse is not true. You have critical points which are not local extrema, as we will see. But this is why looking at places where the gradient vanishes it may point us towards the analysis of minimization and maximization. So there's a small side note about global extrema, which just says that if the domain of a given function is closed and bounded, then global extrema for the function always exists. Closed and bounded thing is not formally defined, but whatever you can, when you think of the words closed and bounded, whatever you feel, you can just take it as that. And most of the times the questions will not be concerned with such things.
Sir, will you please explain the previous point? I couldn't get it.
Which one? This one?
A local extreme of scalar value multivariable functions are critical.
So if, again, think of it as, think of the case of a one variable calculus. If you have a differentiable function for which the maximum or minimum is attained, at this point you have f prime a is equal to 0, correct?
Yes, sir, that I could.
Similarly, I'm not again giving a proof of the fact, but I'm just stating it as a fact that in here you'll have a linear graph or a curve as a graph. For multivariable function, for example, for two variable functions, you will have some sort of surface as a graph, correct?
Yes.
Think of the surface that looks like this. This will be a point where of local maximum for the graph. So at this point, the gradient will be 0, is what I'm saying.
The
So
thing
if
I
you
couldn't
have,
get the point is, however, the converse is not true. That line I couldn't get. This line I couldn't.
that we'll see later. So there are places where the the gradient is 0, but the function is neither maximum or minimum locally. It's saddle points and so on.
Okay.
So you can have saddle points. So the gradient vanishes does not imply minimum or maximum, but minimum or maximum necessarily says that it's a critical one. That's what I was saying. So a note on global extrema. If you want to find the global extrema for a given bounded and closed domain, then what you need to do is analyze critical points on the interior, because typically for partial derivatives, if you have, let's say, a domain which looks like this, at this point, you cannot really talk about x partial derivative or even y partial derivative. It's just along the boundary. So the whole neighborhood is not there. For interior points, you have the behavior in a neighborhood. So you can do, the gradient, continuity of the gradient, all the results that you have seen previously, you can apply. So first you have to treat interior points separately, and then points on the boundary separately, and analyze them. So I don't think I can take up an example for this, but I'll tell one of the TAs to take up an example to specifically illustrate this one. Now the second last thing would be higher order partial derivatives. In the model thing, that is the one-dimensional case, if you have a derivative of a function, now the derivative of a function is itself a function of one variable, right? So you can take second derivative, third derivative, and so on. I mean, not always. You need to have certain nice properties. There are functions which are exactly k times differentiable and so on. But whenever you can, there is a notion of higher order derivatives. But for a multivariable function, partial derivatives itself is a vector, like it's a gradient is a vector valued function. Now, what does it mean to say the second order derivative? The first order derivative, instead of a real number, as in the case of one variable calculus, it was a vector, which is given by the gradient, wherever it exists. Now, if you take each of the components of the gradient, which are just partial derivatives, and take partial derivatives of that, then what you get are called the second order partial derivatives. Example, x squared plus sine, just something. Maybe we'll have to do some this, otherwise it will be trivial. Now, suppose my f is given by this nice function. It is there's no points where weird behavior happens. What is fx? Fx at xy, but I'm not going to write that. This is just 2xy plus y cos xy. Correct. Now, this is a function of x and y. Now, if I take the y derivative of this, that gives me fxy. So it is the y derivative of fx, or fx y, which we write as fxy. Now this would be 2x plus cos xy plus or minus. It would be minus xy sine xy, something like this. There might be some computational errors, but modulo that, you understand what is happening, right? You have to take the derivative, partial derivative with respect to one variable first, and then take, I mean, you can take fxx also, you can use the same variable, but in any case, you'll take partial derivative of the partial derivative wherever it is possible. Like here, it is possible because these are all infinitely differentiable functions. If it has weird behavior, then again, you have to take limits wherever applicable. And the derivatives that you get, or the numbers that you get after all this, these are for second order partial derivatives. So xi xj means first you have done an xi derivation, partial derivation of f, and then the resulting function you have taken the xj derivative of. While writing it in this form, it would be dou square f by dou xj dou xi. So it's like dou by dou xj of dou f dou xi. So here the I will come in the right and j in the left, but here I will be in the left and j in the right. But it's self-explanatory, the notation, and it should not cause confusion. So why are we looking at these partial derivatives of partial derivatives? Because we know that in the case of local extrema, the second derivatives do shed some light. In the case of one variables, for example, if your second derivative was positive, then it's a minimum. If it's negative, it's a maximum. If it's zero, it's a saddle point. So some similar thing happens over here. But there is a problem which was not a problem in the one variable case, where there was no notion of mixed derivatives in the case of one variable. There's only one variable, so you just keep differentiating it with respect to that variable. But in the case of multivariable calculus, whether you differentiate with respect to xi first and then xj first, or xj first and then xi, that makes a difference. And that makes a difference. I mean, that may make a difference. And we would like to work with functions only for which that order does not matter, for reasons which are beyond the scope of this course. So, but we are interested in functions which satisfy this property. And what guarantees this thing is that second order partial derivatives of f exist and are continuous. Now you have to check the continuity of the partial derivatives of second order. Right. So if it's a weird function, it is, you have to do it twice and then check the continuity of that. But this is a theorem which is mostly there just for, your information, and the functions that you're given will be very nice functions which will be infinitely differentiable. So this is not that much of a concern. But this is a very important thing to know. It's a good thing to know. Yeah, is there a doubt?
Sir, the mixed partial derivatives are equal if this condition is satisfied, sir. The
Yes.
f exists and continuous.
Second order partial derivatives must exist and must be continuous. Yes. Then this
Mixed partial derivatives are equal. For second order only, or third order, fourth order?
This is second order. There might be a higher order result in this direction. Like you'll have say third order partial derivatives of f exist and continuous. Then the third order mixed derivatives will all be continuous. There might be something like that. I'm not sure.
Will it be extended to this theorem, or
I don't know. I'm not 100% sure. It seems true.
Only second order.
But I'm not 100. Yeah, we are concerned only about second order because we are concerned about the symmetry of the Hessian matrix, which we will see now. But I'm not sure if it is extendable to more higher dimensions.
If it is symmetric, then only the mixed partial derivatives are equal. No, otherwise, even if it is a continuous.
No. If the mixed partial derivatives are continuous, then this Hessian matrix is symmetric. I mean, it's an if and only. Yeah.
If it is not symmetric, sometimes it may be mixed partial derivative may not be equal. No.
Yeah. So
x and y
symmetry
are
of the Hessian matrix and equality of the mixed partial derivatives are equivalent statements. So we want symmetry of the Hessian matrix. That is why we want, which is equivalent to saying that we want equality of mixed partial derivatives, which is why we require that second order partial derivatives of f exist and continue. Or we require that theorem to have symmetry of the Hessian matrix. Why do we need the symmetry of the Hessian matrix is again a slightly advanced point, which I'm not going to touch on. Now the Hessian matrix, so yeah, partial derivatives of partial derivatives. When you talk about partial derivatives of partial derivatives, there are n choices in the first step, there are n choices in the second step, right? So you get n square many mixed partial derivatives, and the matrix that you get by putting them all together, this is called the Hessian matrix, whose ijth entry is fxjxi. fxjxi or fxi does not make a difference if the function satisfies the hypothesis of Claru's theorem, which we will be mostly dealing with only functions like that. So we'll be dealing with only functions for which Hessian matrix is a symmetric matrix, meaning fx2 x1 or fx1 x2, it doesn't make a difference. And the Hessian test which is using the Hessian matrix to analyze behavior of critical points. Just like using the second order derivative to analyze the critical points in one variable, we use this matrix instead of just one real number. A real number being positive, mean, minimum, all that does not happen. Here we have to have some properties of the matrix, and let's see what those properties are. Yeah, so we'll, as I said before, okay. Hessian test also will be giving the conditions only for 2-variable and 3-variable functions. The rest is, I mean, the other things are much more complicated, as you will see. For 3 itself, it gets pretty complicated. There are 3 cases, I mean, 4 cases as is written over here, but determinant is positive of the Hessian matrix, gives you local extrema. Determinant is less than 0, gives a saddle point. And the determinant equal to 0 means that the test is inconclusive. So you may have a local extrema for which the Hessian test does not give you the fact that it is a local extrema. So the Hessian test is not, it does not work always. If determinant is 0, it fails. So if determinant is 0, it does not mean that your critical point is not a local extreme. This is again another point of caution. There are functions for which maxima or minima are attained at some point, even global sometimes, but the Hessian test is inconclusive. But when the determinant is non-zero, then definitely you can conclude something. If it is negative, then it's a saddle point. Then if determinant is positive and the first entry, the leading entry is positive, then it's a local minimum. The determinant is positive and the leading entry is negative, then it's a local maximum. And for 3 variables, the conditions are the following. First of all, the hypothesis of Clairaut's theorem has to be satisfied, meaning second order partial derivatives must exist and they must be continuous. And then these are the conditions. So once again, as in the case of 2 variables, if determinant is 0, then the test is inconclusive. If the determinant is, well, here it is better to look at a diagram. You look at a 3-variable function, you'll have fxx, fxy, fxz, fxy, fyy, fyz, and then you have zy, zz. Right, this is your Hessian matrix. I'm not writing at a tilde everywhere. When do you conclude that A is a local minimum? This is how you have to see it. You look at this 1 cross 1 matrix, that is just the first entry. That is just f of x, fxx. Now, fxx is positive. Then you look at the leading 2 cross 2 matrix, which is fxx, fy, fxy, fxy, fyy. You look at the determinant of that. That is fxx, fyy minus fxy square, which is over here. So this thing is determinant of the leading 1 cross 1 matrix. This is the determinant of the leading 2 cross 2 matrix, submatrix. And this is the determinant of the whole matrix, which you can also think of as the determinant of the leading 3 cross 3 matrix. If all of these are positive, if you have plus, 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 then it is minimum. And then you have minus, plus, minus, which means fxx is negative. Then determinant of the 2 cross 2 matrix is positive. And then the determinant of the whole thing is negative. This is some alternating behavior. So minus, plus, minus. Then it is a maximum. Now, if determinant is not 0 and these 2 cases don't happen, then it is a saddle point. So this is how you check for the Hessian test for a function of 3 variables. Is that clear?
Yes, sir.
So here what do we have? Here you have fxx, fxy, fxy.
So these are quite of identical because here we don't have that. We end at 2 by 2 only.
Yes, exactly. So if this is positive and positive, then it is a local maximum. If it is positive and negative, sorry, if it is negative and positive. So if here you have plus plus and minus plus, right?
Yes.
Then you have that, and but there's a little bit of caution that you have to take, that if determinant is negative is not there, but here you have certain things. I mean, it follows the same kind of argument, but just remember it this way. Plus 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 is okay, minus plus minus is okay. Even there, plus plus and minus plus is okay.
And sir, if we want
Everything
to
else is sad, huh?
if we want to look into this in our own free time, the proofs of this that require are they too
If
beyond
you
undergraduate level?
know eigenvalues, you can probably understand the proof.
Okay, so that will come in the next course. So then we,
Okay. Then it is probably better to postpone even that interest for that time, because this uses eigenvalues. As far as I know, I don't remember the proof exactly, but the way it is formulated, it screams eigenvalues.
Sir,
Yeah,
uh, like if we have fxx is equal to 2x, right? Let's say hypothetically.
just a minute. F xy is equal to
No. What I'm trying to say, let's say we have a double
okay,
derivative of any function fxx
okay,
is
okay,
2x, right?
is to x. Okay.
Yes. And we need to find, let's say, at any arbitrary point, let's say minus 1.
No, this is a function of two variables or three variables.
No. What I'm trying to say, like in order to determine it is maxima or minima, we need to only see at fxx, right?
fxx at that point. Yeah. So for example, if your function is a three variable function, you will have some a, b, c.
Yeah, of course. Let's say anything now. You can take any value.
Okay, let's take something like 3 to 1 in this, in which case this will be 6.
So what you can conclude, like 6 is greater than 0. Then
6
why
is
you
greater
keep
than
this
0.
kind of stuff? I didn't even get it. What is plus 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 and this?
No. You just need, you only fxx is not enough. You need fxx, then you need this fxx fyy minus fxy square also to be greater than 0, which is the determinant of this 2 cross 2 matrix.
Oh
And
my.
then
Okay, got it, sir. And then the
and then
determinant
the
of entire matrix.
determinant, which is like the 3 cross 3 matrix. So there's a 1
Okay.
cross 1 step, there's a 2 cross 2 step, there's a 3 cross 3 step. If all of those
Okay.
are positive, the determinants
Got
of those matrices. If all of those are positive, then it's a minimum. If it is
Okay.
negative, positive, negative, then it's a maximum, local maximum.
Thanks a lot. Okay.
Sir,
That's why I'm confused a little bit.
how to find the critical points of that function of three variables, fx equal to 0, fy equal to 0? Is it fz equal to 0?
You have to just solve this.
That means
Since
fx
this
equal
is
to 0, fy equal to 0, fz equal to 0. Separate.
yes.
Okay.
Each of them have to be equal to 0.
How much more
Then,
left?
sorry,
How much more left the content?
this is the last slide.
Okay.
Yeah. And this is also more of just rounding out things. Differentiability is an important concept. And to check whether something is differentiable, you have to evaluate this limit. So once again, you can draw the parallel to the one variable case and check it for yourself. But here I'm not going to do that. Instead of taking a tilde plus hei, where h is a scalar, we now change the function value by arbitrary vectors, right? We just, this h is a vector. Maybe it would have been better if I put tilde as over here to emphasize that these are vectors and not scalars. So change the function value by that, and there is this extra term, which is given by, of course, differentiability. To even talk about differentiability, you need the existence of the gradient or the partial derivatives. If the partial derivatives exist and this limit is equal to 0, then your function is said to be differentiable. If not, it's not. And typically, how you would solve problems which ask for whether something is differentiable or not, you set up this equation. You first find out the partial derivatives, then set up this equation or this quantity, f of a tilde plus h tilde minus f of a tilde minus gradient dot with h tilde divided by norm of h. So, okay, maybe norm was given by 2 things, yeah? Norm of this vector. So you cannot divide by a vector, right? Vector divided by a vector, you cannot do a scalar divided by a vector. So you have the norm of that vector that goes to 0. And that quantity, you have to analyze the limit of that as h tilde goes to 0. And what does a vector going to 0 mean? Once again, we have seen what it means for h tilde to go to 0. You have to say that along all possible curves, this thing goes to 0, or use things like sandwich principle. And you have to use things like sandwich principle. It is not possible to say that along all curves, this quantity goes to 0. All right, so that is the last concept. And this is where we'll stop.
Sir,
Problems will be discussed in TA sessions.
sir,
Yeah.
in real number system, the derivative is just it is not equal to 0. Why it is here equal to 0? The limit is equal to 0. It is
So,
there equal to f dash of a equal to it will come like that. Why?
So this is in the real number system. It is this, right? This is your f prime a.
Yeah.
So limit as this h goes to 0 of this would be f prime a.
Yes.
Right. So there's a limit over here. I'm just skipping that for now.
Yeah.
Now, if I take this to this side, wait a minute. I'll get minus f prime a h is equal to 0. Right. Is it not the same?
Okay, understood, sir.
Once again, if you find this to be more convenient, you can look at the one-dimensional case and see that f prime a is just replaced by gradient. So the gradient is the higher dimensional analog of the derivative, and many cases you can get the corresponding notions in higher dimensions by just replacing your derivative with the gradient.
Why we take modulus of h here, the denominator?
What if you just take h? I mean, if you take just h, you are dividing by a vector. So is there a way to divide by a vector? H is a vector over here. There's nothing like that, right? So here you're once again, when you take derivative or differentiation, you have to measure it with respect to change in input. Now the change in input here in this case is just h, but h itself is a vector, so you take the magnitude of the change.
Okay. Okay, sir.
Yeah.
Sir, one small doubt, sir.
Yes.
What by when you say Bell behaved function? Okay, can you just can conclude from?
See, in this case, strictly speaking, you don't. So, are you talking in the context of
Yeah,
that nice enough function, partial derivatives? You can use
Yeah.
direct thing. There,
Yes, sir.
you very strictly speaking, you don't even need well-behavedness. That is a property in general that is true. That you can differentiate it with respect to. Okay, I don't know if I want to get into this thing. But for your purposes, just think of well-behaved as something that does not involve denominators which go to 0, and they are written as sums, products, and compositions of well-known trigonometric exponential polynomial functions. You can just You can just leave it at that.
Okay, okay.
And, yeah.
Thanks a lot.
Yeah. And yeah, if there are specific doubts that you want to talk about, you can stay back. Otherwise, feel free to leave.
So, excuse me, sir.
Yeah.
So I have one question, but not related to this. Do we have an graded assignment for week 12, or is it not there?
I don't think there is one.
Okay, because
Um,
the grading pattern document mentions that there is one and that we should submit. So I was just
Oh,
cross-checking that.
okay. I'll inquire with Lavanya and I'll let you know. But as far as I
Actually,
know,
the
there
grading
is
pattern document says that it is not. I mean, it won't be considered for final scoring, but we should still submit it since week 12 is part of the syllabus. But it is
okay,
not there
okay.
in the portal yet.
Well, the week 12 content also is just
Yes,
there's
sir. Repeating
nothing.
content are repeated.
It's just week 11, right? So I don't think there is anything.
Okay, okay,
But
sure, sir.
anyway,
Thanks.
I'll verify that, and in the next session, I mean, I won't be taking any more sessions, but I'll tell someone to send a message across.